Have you ever stared into the night sky, at the darkness between the stars, and wondered what lies beyond that blackness? Not the stars themselves, not the galaxies we can see, but the void, the unseen, the unspeakable depths. Somewhere out there, among the drifting light and cold silence, is something that doesn't reflect or emit anything at all. A black hole, silent, invisible, and yet powerful enough to trap even time itself. And now imagine this: you are drifting toward it, not in a spaceship, not as a distant observer reading equations or watching simulations, but you, yourself, are falling. There are no alarms, no explosions, no screams, just gravity, relentless, absolute, drawing you in. The question is no longer abstract, it's personal, immediate, not in theory, not as metaphor, but truly, physically, fundamentally. What happens when a conscious human being crosses the threshold of a black hole? Do you die instantly? Are you stretched into atoms, lost forever? Or does something else happen? Something that no human has ever lived to describe. Today, we explore that question. With all we know from general relativity, quantum physics, the paradoxes that haunt our deepest models, and the possibilities that some scientists whisper but dare not yet declare. This is not science fiction. This is science reaching toward its edge. You are falling. The stars behind you begin to warp. The light ahead dims into nothing. Time no longer feels like time. And now, we begin. In the vast theater of the cosmos, stars are born, burned, and die. Most fade into white dwarfs or explode into supernovae. But a rare few end their life cycles in a collapse so extreme that even light cannot escape. What remains is not a star. It is something else entirely. Something we call a black hole. For decades, black holes were only theoretical and mathematical solutions within Einstein's general theory of relativity. But today, we have not only evidence, they have become central to our understanding of gravity, time, and the very fabric of space itself. So what happens when something falls into one? That question has puzzled physicists since the concept of black holes was first understood. It's a question of physics, but also of perception, of time, of the nature of information, and ultimately, of reality itself. To understand the journey into a black hole, we must begin not at its edge, but far away where space is still familiar. Imagine an object, a spacecraft perhaps, approaching a black hole. To an external observer, it seems to slow down as it nears the event horizon, the invisible boundary from which not even light can return. The light coming from the object becomes increasingly red-shifted. Eventually, it fades completely from view, but from the object's perspective it continues to fall. It crosses the event horizon without noticing any obvious boundary. It experiences no sudden shift, no abrupt sensation, yet at that point no return is possible. This region beyond the event horizon is where our current understanding becomes speculative. According to Einstein's theory, the object would continue to fall toward a singularity, a point of infinite density and zero volume. But infinity, in physics, is often a sign that our models are incomplete. And here, quantum mechanics enters the scene. Quantum theory holds that information is never truly lost. Yet, if a black hole absorbs matter, including all the information it carries, about its structure, energy, even its quantum state, and if that matter is destroyed at the singularity, then where does the information go? This conflict between general relativity and quantum mechanics has become one of the central problems in modern theoretical physics. It's known as the black hole information paradox. Stephen Hawking, who first proposed that black holes emit faint thermal radiation, now known as Hawking radiation, believed that this radiation carried no information about the material that fell in. According to this view, over time, the black hole would evaporate completely, leaving no trace of what it once consumed. But many scientists disagreed. Leonard Susskind, among others, proposed that information might be preserved, not lost, perhaps encoded on the event horizon itself. This led to the idea of the holographic principle, the notion that all the information about a volume of space can be described by a theory that lives on its boundary. If true, this would revolutionize our understanding of not just black holes, but the nature of reality. Others, like Roger Penrose, proposed that singularities might not be endpoints, but gateways. Possibilities such as conformal cyclic cosmology suggest that black holes may play a role in the birth of new universes. But what does this mean for something, or someone, that falls in? Would you be destroyed instantly by tidal forces? That depends on the black hole's mass. In smaller black holes, the gravitational gradient, what we call spaghettification, would stretch and compress an object violently. But in supermassive black holes, the gradient is so gentle that you could cross the horizon without noticing. At least, at first. As you fall deeper, time would become distorted. From your point of view, you would fall normally, but for outside observers, your image would appear frozen near the edge, stretched and dimmed by gravitational redshift. You would remain visible in some form for what appears to be an eternity. Does that mean you're alive, from their point of view, or gone? Inside, time and space swap roles. Forward becomes inward. The singularity is no longer a location in space. It becomes your future. No matter what you do, you move toward it. You cannot escape it. It is, quite literally, your destiny. What lies at the singularity no one knows. Our physics stops working there. Some theories suggest that quantum gravity, a yet undiscovered framework combining general relativity and quantum mechanics, will resolve the singularity into something finite, something understandable. Others propose that black holes could connect to white holes, hypothetical time-reversed black holes that expel matter instead of absorbing it. These ideas fall under the broader category of wormholes, bridges through space-time predicted by Einstein-Rosen equations. But so far, they remain speculative. Still, they raise profound questions. Could black holes be portals, not just graves? Could falling into one mean entering another universe? Could it mean rebirth? And perhaps the most unsettling idea, are we, ourselves, living inside something that once was a black hole? This is where quantum theory must step in. According to quantum mechanics, information, the fundamental encoding of what things are, their structure, state, and configuration, cannot simply vanish. Yet, in the heart of a black hole, general relativity tells us that all known physical quantities are crushed to zero volume and infinite density. So what happens to the information of the things that fall in? This contradiction is known as the black hole information paradox, and it has puzzled physicists for decades. If you, with your memories, your structure, your atoms, your quantum state, were to fall into a black hole, where does the information that makes you go? Does it disappear forever, violating quantum laws? Or does it linger somehow, encoded at the boundary, preserved in a way we have yet to fully understand? Stephen Hawking famously proposed that black holes aren't entirely black. In 1974, he suggested that due to quantum effects near the event horizon, black holes could emit tiny amounts of thermal radiation, now called Hawking radiation. Over immense timescales, this would cause the black hole to slowly lose mass and evaporate. But if it evaporates completely, what happens to all the information that fell in? Is it released in the radiation? Is it smeared across the event horizon, encoded like a cosmic hologram? This question has led to profound ideas, including the holographic principle, the notion that all the information inside a volume of space can be described by information on its boundary, much like a 3D object encoded in 2D. Now, pause for a moment. Consider what this really means, that your entire existence, once fallen into a black hole, might not be lost, but flattened, stretched, and encoded onto a surface, perhaps forever. A frozen record of every atom and every thought, written in quantum handwriting on the very edge of oblivion. Others have proposed different ideas. Maybe black holes don't destroy information, but instead transport it elsewhere. Maybe the singularity is not the end, but a bridge. This brings us to the tantalizing hypothesis of wormholes. Solutions to Einstein's equation suggest that black holes might be connected to distant points in space and time via hidden tunnels, Einstein-Rosen bridges. If true, and if such wormholes could be traversable, then falling into a black hole might mean emerging somewhere else in the universe, or even in another universe altogether. Of course, every current model tells us such journeys are blocked by instability, radiation, and tidal forces. But the mathematics whispers the possibility, and physics has a way of turning whispers into revelations. Still, the reality remains harsh. Most likely your fall would be fatal. The tidal forces near smaller black holes are so extreme that you would be stretched into a thin filament of atoms, an effect known as spaghettification. But with a supermassive black hole, millions or billions of times the mass of the Sun, the event horizon is vast and tidal forces less intense. You could cross it without immediate harm. You would not notice the moment you pass the point of no return. But even then, even if death is delayed, it is not avoided. At the singularity, the future ends. Unless it does, there is a growing body of research that suggests something deeper: quantum gravity. The elusive theory that must unite general relativity and quantum mechanics may resolve the paradoxes we now face. Some approaches, like loop quantum gravity, suggest the singularity might be replaced by a quantum bounce, a compressed state that eventually expands again. Others point to the concept of firewalls, hypothetical walls of energy at the event horizon that burn up anything falling in, preserving information at the cost of destroying the falling object. But this violates the equivalence principle of general relativity. You see, we are trapped between two unyielding principles, each screaming a different truth. And then there's the most philosophical proposal of all, that what happens inside a black hole is not a question of physics, but of perception. To you, falling in, time continues. To the outside universe, you freeze at the edge. Reality itself seems to diverge depending on the observer. Maybe the fall is not about where you go, but about which truth you inhabit. The universe, at this level, is not just physical, it is related. So what if falling into a black hole is not the end, but a transformation? Some physicists suggest that black holes might not be destroyers, but creators. That every black hole births a new region of space-time, a new universe cut off from our own. This idea, called cosmological natural selection, imagines that black holes are like seeds of cosmic reproduction. If true, then falling into one might mean becoming part of something infinitely greater. A new cosmos with its own stars, its own laws, perhaps even its own observers, born from the collapse of yours, and yet we must be careful. These ideas, though founded in equations and logic, are still untested. We have no probe that can cross the horizon and report back. No signal can escape to tell us the truth. In this way, the black hole is a mirror, not reflecting light, but reflecting our own limits, our fears, our dreams. We cannot know for sure what lies beyond the edge, but we can ask. We can model, we can imagine. So where would you go if you fell into a black hole? You might be torn apart by tides or preserved as holographic code. You might vanish or be reborn. You might witness the end of time or the birth of another. You might dissolve into the quantum foam that underlies all of existence. Or, perhaps most unsettling of all, you might go nowhere. You might remain there, forever falling, frozen in the fabric of space, a ghost in the mathematics of space-time. This is what makes black holes so haunting, so beautiful. They are not only the graveyards of stars, but the crucibles of theory, where our best understanding of the universe is tested, and where it fails, where paradox lives, and where discovery waits. Each black hole is a silent challenge, daring us to look deeper, to think harder, to reach further. And as we stare into that darkness, we are forced to ask not just where we go, but who we are, what it means to know, to observe, to exist. For perhaps at the center of the black hole, the truth is not a place but a question, and maybe the fall itself. Into mystery, into wonder, into the unknown is the answer we've been chasing all along. Thank you for joining us on this journey into the heart of the unknown. If you found this exploration as thought-provoking as we did, consider subscribing for more voyages through time, space, and the frontiers of human understanding. Until next time, stay curious, stay questioning, and keep